All right. Hello, everybody. I hope everyone in the United States had a great President's Day. And I happen to be Canadian, so I hope all my Canadian friends had an awesome family day yesterday. What a great way to come back from a holiday! Attend a webinar. All right, so today we have a very exciting topic. We'll be talking about advanced material characterization using multi-mode pyrolyzers and 3D printing, also known as additive manufacturing. We'll also talk about smart coatings and nanomaterials. So I'm Lauren Armstrong, Marketing Director for Quantum Analytics, and I'll be your moderator for today's event. I'm going to give a really quick note about Quantum Analytics. We are a value-added distributor of analytical instrumentation in the United States and Canada. We offer an array of flexible instrument financing programs combined with technical services like cross-platform installation, training, and product support. For over 30 years, our company has helped labs get the best-in-class instrumentation they need for a variety of applications, including gas chromatography, Leica chromatography, mass spec, FTIR, XRD, XRF, SIFT-MS, plus a whole range of sample introduction and preparation products, including the pyrolysis technique you're learning about today. Today's webinar will feature two presenters, Regine Belgina of Frontier Labs and Dr. Rigoberto Advincula of Case Western Reserve University. Our first speaker, Regine, is a technical and marketing director for Frontier Labs. As an analytical chemist, Regine has worked with a variety of analytical instruments such as pyrolysis GCMS, TGA, FTIR, and X-rays for material characterization, polymer identification, and contamination analysis. Our second speaker is Dr. Rigoberto Advincula. Dr. Advincula is a professor at Case Western Reserve University in Cleveland, Ohio. He's a fellow of the American Chemical Society, fellow of the Polymer Science and Engineering Division of the ACS, and fellow of the Polymer Chemistry Division of ACS. He is also a member of NACE, SPE, ERG, MRS, and AAAS, and frequently sought out speaker and expert in polymer materials, coatings, and sensors. He is also pioneering a number of 3D printing routes towards new polymer and nanocomposite material properties. All right, so during the Q&A portion of the webinar, we'll also be joined by Dr. Terry Ramus. Terry is an application scientist for Frontier Laboratories with over 35 years of experience in a wide variety of companies and markets with emphasis on analytical chemistry. If you have any application-related questions, Terry is going to be ready to answer. All right, so as a registered guest, you're going to receive a link to this recorded webinar in your email when it becomes available. Type your questions at any time in the question module that you see at the right side of the screen. All right, so this ends our introduction. So without further delay, let's get started. Regine, take it away.
Thank you so much, Lauren, for the introduction. Here is our agenda for today. We'll start with a summary of who we are, then fundamentals of pyrolysis. After that, we will talk about the multi-mode pyrolyzer, its operational mode, and the method map, as well as sample preparation and system configuration. And then we have the application note presented by Dr. Advincula. Frontier Lab was founded in 1991 by Dr. Chusan. Chusan, with the support of polymer scientists at Nagoya University in Japan, developed a pyrolyzer based on a vertical microfurnace design. And we will discuss the characteristic of the microfurnace design shortly. We are a global corporation, and our main products are a series of pyrolyzers, such as the multi-shot and single-shot pyrolyzers, rapid screening reactors for catalyst analysis, and a line of ultra-alloy stainless steel capillary column. Our North American Technology Center is located in California, as shown here. Okay, let's start with the fundamentals of pyrolysis. What is pyrolysis? By definition, pyrolysis is a thermochemical decomposition of organic compounds at elevated temperatures without the participation of oxygen. Most often, an inert gas such as helium is used. In this technique, a sufficient amount of heat breaks down the organic bonds of a complex mixture into smaller and more stable molecules called pyrolytes. Pyrolytes then form, and their relative intensities provide insight into the nature of the original composition. It is very important to mention that applying the sufficient amount of heat and identifying the appropriate temperature for programming the pyrolyzer furnace are critical factors in pyrolysis technique. As we go more into detail, you'll find out how to identify that sufficient amount of heat so you're not over or underheating your samples. How the multi-mode pyrolyzer can expand the capability of your GCMS systems. Substances as shown here at ambient temperature are gas, liquid, or solid, mostly depending on their molecular weights. Materials that are soluble in solvents can be analyzed by GC or LC. Of these compounds, about 30% can be analyzed by GC and about 85% by LC with the proper solvents. However, as you could see here, there are also some insoluble compounds that cannot be analyzed by LC, LCMS, GC, or GCMS. But these insoluble materials can be analyzed by pyrolysis GCMS. In fact, when using pyrolysis GCMS, a solid sample can be analyzed as is, and there is no need for any solvent extraction or sample preparation prior to the analysis. So the entire range of organic materials, from gases to solids, can be analyzed by pyrolysis GCMS. And that's one of the advantages of the multi-mode pyrolyzer and how it can expand the capability of your GCMS systems. So now let's talk about how we can analyze the results obtained from the pyrolysis GCMS. F-Search is a search engine with 4 unique libraries for identifying additives, volatiles, lighter components, as well as oligomers, heaviers, and polymeric compounds. It is commonly used in conjunction with the MS library and allows you to also create your own user library to perform contamination analysis, comparison analysis, good versus bad, deformulation, as well as failure analysis. F-Search has other features like the ability to overlay different chromatograms. You can extract different M over Z ions and integrated sum analysis where the F-Search can actually integrate the whole chromatogram, make an average mass spectrum, and identify the corresponding compounds. This book is also used along with the F-Search. The book has pyrograms, EGA thermograms, and MS data of major pyrolytes for many polymer. It also has detailed information about the peak assignment tables and the EGAs. Here is an example page from the book for pyrolysis GCMS of polyethylene. You can see the pyrogram of the polymer that is performed at 600 C as shown as number 1 category. Number 2 category is the peak assignment table together with molecular weight, relative peak intensity, and the retention index. Number 3 is the EGA thermogram that was performed from 100 to 700 C, 20 degrees per minute, as well as the average mass spectrum of the EGA. And number 4 category is the mass spectrum of the top 10 major peaks. So F-Search is a search engine software that contains all that information from the book. So now let's talk about the multi-mode pyrolyzer and how it works. As the name says, using the multi-mode furnace, multiple analyses can be performed on a single sample. This is really another advantage of the multi-mode pyrolyzer, where its furnace can be used for other analytical techniques in addition to flash pyrolysis. In fact, the multi-mode pyrolyzer can be used for evolved gas analysis, thermal desorption, part cutting, and reactive pyrolysis in addition to flash pyrolysis. We have created a series of techniques referred to as the method map to chemically characterize samples using the multi-mode pyrolyzer. EGA, which is evolved gas analysis, is the first step, which provides a clear picture about the thermal profile of the sample as well as the optimal temperature zones for the next step. So EGA really guides you what to do next. It will show if a thermal desorption, hard cutting, or flash pyrolysis is needed, or if a combination of the techniques is required. To perform EGA, a short and deactivated tube is used to connect the GC injection port to the MS. The sample is dropped into the multi-mode pyrolyzer furnace, which is at a relatively low temperature. The furnace is then programmed to a much higher temperature, and compounds evolve continuously from the sample as the temperature increases. A plot of detector response versus furnace temperature is obtained, as you could see in this figure. So the x-axis is the furnace temperature, as well as the retention time, and the y-axis is the intensity. After obtaining your EGA thermogram, you can analyze the peaks using the FSearch EGA MS library. If it's needed to further analyze the sample, then EGA guides you to the next step. You can perform thermal desorption, which is used for analyzing additives and volatiles. However, the key point here is that you are thermally extracting all the additives and volatiles from the mixture. So any sample preparation or solvent extraction step is eliminated. You could also perform flash pyrolysis, which is also called single-shot GCMS, and is the fundamental technique for polymer analysis. In this mode, the furnace is typically programmed at high temperature to break down the polymeric and heavier compounds into smaller fragmentations. The key here is that you are performing a continuous pyrolysis, where the sample is not subjected to heat prior to the pyrolysis, as opposed to a pulse mode pyrolysis where the sample is subjected to heat before the analysis starts. You can also do a double shot analysis as shown here, that is performing two analyses on one single sample, thermal desorption followed by flash pyrolysis. So first, the additives and volatiles are thermally extracted from the mixture, and you obtain a thermal desorption chromatogram. And then the flash pyrolysis is performed to analyze the heavier and polymeric compounds from the pyrogram. You can also perform hard cutting, which is the multi-steps thermal desorption and pyrolysis. So in this case, the EGA thermogram is sliced into multiple temperature zones depending on the thermal profile obtained from the EGA. So this is the flash pyrolysis or single-shot GCMS. As shown here, the EGA was first obtained to identify the optimal pyrolysis temperature, in this case 600 C. To perform the flash pyrolysis, the EGA tube is then switched to a separation column using the GCMS vent-free adapter. The vent-free adapter allows you to change the columns without venting your MS and waiting for it to be pumped down. So it saves lots of time and increased efficiency in your lab. Flash pyrolysis then generates a pyrogram that is a mixture of all the additives, lighters, and heavier polymeric compounds. And as we mentioned, using the FSearch additive and polymer libraries, you can now analyze the compounds and pyrolytes from the pyrogram. This is the double shot analysis, which is the thermal extraction of additives and volatiles from the polymer. First, the EGA is performed, in this case 100 to 720 degrees per minute, and as shown here, the EGA thermogram is obtained. To further analyze the peaks from the EGA tube is then switched to a separation column using the vent-free GCMS adapter. Then the furnace is programmed from 100 to 300 C, 20 degrees per minute, to obtain a thermal desorption GCMS chromatogram. that corresponds to any residual solvents, monomers, additives, volatiles, and lighter components. And then the second shot is the flash pyrolysis, where the furnace is programmed at 600 C in this case to analyze the heavier and polymeric compounds from the obtained pyrogram. So this is called a double shot because you are performing two analyses on one single sample, thermal desorption followed by flash pyrolysis. So now let's talk a little bit about hard cutting in more detail. Hard cutting is thermally slicing the EGA thermogram into multiple temperature zones to obtain separate GCMS chromatograms. This mode of operation is a very powerful technique for deformulation, reverse engineering, as well as failure and comparison analysis, because you are able to analyze the composition of a mixture in detail. On the right-hand side, you can see an EGA thermogram of an eyeliner that can be sliced into 5 different zones or peaks, zone A to E. The hard cutting technique allows us to program the pyrolyzer furnace into 5 temperature zones in this case, and obtain separate GCMS chromatograms to identify the components in each thermal zone. So the analysis of each thermal zone yields a chromatogram containing only those compounds evolving from the sample of the selected range. Figure on the left shows each zone and their corresponding identified components. Selective sampler, also shown on the right-hand side, is an accessory that is used for hard cutting technique. From the figure, you can see that selective sampler allows you to selectively pick and choose which thermal zones of your EGA thermogram you are interested to obtain the GCMS chromatogram, and which one or ones you want to vent and not send to the GC column. Sample preparation in pyrolysis GCMS is very straightforward and simple. Depending on your sample type, if it's a liquid or solid, you can just use the appropriate sampling tools and place your sample into the sample cup. So samples can be analyzed as is. No need for any sample preparation or solvent extraction prior to the analysis. Here we have the system configuration for pyrolysis GCMS. One key point that I like to mention here is the fact that the pyrolyzer is directly connected to the GC injection port. So there is no transfer line that can result in any contamination or losing some of those lighter components. Lastly, let's talk about what sets the vertical microfurnace design apart from others. So sample introduction is nearly instantaneous. The sample is placed in the sample cup and is held at near ambient temperature in helium. The microfurnace is then preheated to the desired temperature that is precisely measured with a thermocouple sensor. The sample cup then drops into the quartz pyrolysis tube where the sample is pyrolyzed in less than 20 milliseconds. The pyrolytes are then swept onto the GC column for separation and detection by DMS. So this technology is based on a continuous mode pyrolysis, where your sample is held in an ambient temperature while the furnace is preheated. So the sample does not get exposed to any heat prior to the analysis. As a result, there won't be any degradation or evaporation of the lighter components prior to the analysis. That's all I have for today. Thank you so much for your attention. Now I would like to pass it on to Dr. Advincula for his application notes.
Awesome. Thank you so much, Regine. Dr. Advincula, I'm going to make you the presenter.
Thank you so much, Rogine, for that nice introduction on the GC-MS pyrolysis technique with Frontier Labs. In collaboration with Quantum Analytics, I would like to present our work on 3D printing and other types of high-performance nanocomposites and elastomers. And of course, I'd like to thank our host, Lauren, for the introduction. And after this talk, I'll be happy to answer any questions together with Rogine and Terry regarding other techniques and applications of GC mass spec pyrolysis. So to begin with, I'm a professor at Case Western Reserve University. This is a comprehensive major research university in Cleveland, Ohio. And in a nice summer day, it looks like this, although winter months, you can imagine everything is blanketed with snow. But it's a cultural center. We have the Cleveland Museum of Art, the famous Cleveland Orchestra, and we are a city by the lake, Lake Erie. Now, Case Western is also the home of ThinkBox, one of the first makerspace additive manufacturing 3D printing laboratories located in a major university. And it is very accessible to our students, but more so open to the public as well as faculty doing research in 3D printing. My department, I'm with the Macromolecular Science Engineering Department, that is polymers or plastics for short. We specialize on materials that end up in paints, plastic packaging, coatings, and even 3D printing. Some of my research work are very basic, and as you can see here, a collage of the different research areas we have contributed in interfacial chemistry, patterning, detection methods, surface analytical methods, and nanomaterials as well. On the other hand, as a group, we are very versed in working with industry. We like to use the platform, the best basic platforms that the university can offer to help solve problems, offer new technologies, and provide a cost performance ratio benefit to the companies that we work with. And as you can see here, we look at a bridge based on applied science or what we call engineering to link up with the market. And of course, working with a company or an industrial problem or even a startup company allows us to take this basic platform and productize it or solve problems which can improve efficiency. After all, it is all about performance and cost ratio, and of course, somebody willing to pay for that work. Now, in our case, we have a complete laboratory, as you can see here, for doing a lot of polymer analysis, rheology. Specifically, we have a lot of thin film coating methods, even fabrication methods, spectroscopy, microscopy, as well as has been introduced to you recently by Rogine, capabilities now together with Frontier Labs and Quantum Analytics to do GC mass spec pyrolysis. In fact, we organize a number of conferences. The nearest one will be the Advanced Coatings Conference on May, and also a 3D printing conference in October this year. You can take note of the websites and get more information. Both conferences are in partnership with Frontier Labs and Quantum Analytics as sponsors. Now, let me tell you more about coatings and its impact in terms of packaging, consumer electronics, automotive, finishing. Although I will not be able to talk much about coatings in general today because that is a separate topic, I can tell you, of course, a gamut of projects we have done in the past where trying to improve the structure property relationship or looking at new function that can be improved, let's say by nanostructuring or super hydrophobic properties, allow us to be at the frontier of materials development as well as improving property of products. And all of this means that we have to be versed with the chemistry, interfacial chemistry in particular, with a number of these coating applications. For example, we look at nanostructuring at the layer by layer level, which means we can apply chemical adsorption or physical adsorption to modify properties and layers. We have developed a number of techniques involving polyelectrolyte modification or even the use of polymer brushes. Polymer brushes allow us to graft polymers covalently on surfaces as well as improve their wetting behavior. On the other hand, our group has contributed a lot in the area of organic electronics, or sometimes more familiar to you as OLED display devices that is found in your Samsung, let's say, smartphones. After all, this is all about polymer science. Polymers, as you most commonly know as plastics, really goes beyond the term plastics. This comprises the chemistry that is involved in thermosets and elastomers, or commonly known as epoxy or paint, or rubber, or different formulations that goes into shampoo, personal care, and other consumer products. What the control of polymer interface and colloidal science does is it enables us to nanostructure their function on surfaces as coatings or membranes, or as additives that eventually goes to your shampoo or medicine by controlling the interaction as a colloidal particle. That means that this type of study or optimization brings us at par with control of other nanomaterials as shown on the right. And that brings us a segue to using nanomaterials such as carbon nanotubes, graphene, vacuum dots, nanocellulose, together with polymer science to improve many types of material properties. Now, key to some of our experiments is determining the composition, the structure property relationship of the materials that we develop. Shown on the left are some of the more recognizable consumer products, or in particular industrial applications: plastics, inks, rubber, coatings, composites, adhesives, lubricants, chemical additives, surfactants, and formulation. This collage of or list of rather consumer products actually is based on formulation or blending science. So many of the industrial and consumer applications we have are actually mixtures or blends of many compositions. That is why GC mass spec pyrolysis is so important in things like reverse engineering or understanding failure of products, or even trying to understand how certain additives or compositions are applied and therefore synergistically enhance performance. And the techniques that was featured and described by Rogin using the pyrolysis GC mass spec of Frontier Labs together with very good uh, GC mass spec instrumentation allows a very keen, a very smart analytical chemist to do a lot of this analysis and contribute to development of these products. So in shortness of time, I will not be able to explain many things on coatings and composites that we actually do together with these techniques, but rather I'll just focus today on a very interesting and of course hot topic in the area of 3D printing, which in this case you will learn more about 3D printing today, as well as some of the applications we have used with GC mass spec pyrolysis to analyze some of the commercial polymers that we 3D printed. To begin with, let me introduce to you 3D printing as a perspective. Back in 2016, I was invited by the World Economic Forum to give a perspective on the future of 3D printing. 3D printing today is part of manufacturing, prototyping, but the perspective of the growth of 3D printing is that plastics, polymers, ceramics can play an important role in robotics, soft robotics, automotive, aerospace, and in the future, of course, to outer space or inner space, bio-inspired design, and of course, biomedical applications. And vital to this is the use of the right materials together with the appropriate design. The combination of the two makes 3D printing uh, the manufacturing mode of the future and Industry 4.0. Now, today, one can buy a commercial 3D printer, even a hobbyist 3D printer, such as on the left, costing anywhere from several hundred thousand to $1,000, or the use of, let's say, carbon technology for fast 3D printing and even high output, high throughput 3D printing. I will introduce these methods to you in summary so you can have an appreciation of the different uses and scale. But what I actually like about 3D printing is that we can be inspired by nature, or biomimetically, we can copy nature. And in fact, there's a growing movement of taking what is present and available in nature to design new mechanical and thermomechanical uses that goes into the design of functions for robotics, for furniture, for architectural implements, and so on. Another is that 3D printing allows us to go from micro to nano resolution. In fact, my introduction with 3D printing more than 20 years ago was actually based on stereolithography using two-photon polymerization. And as you can see here, 3D printing goes to the scale where you need a microscope, a stereo microscope, or even SEM to see the fine details that can be done by stereolithography 3D printing. Another case is the growing need for prosthesis devices or methods of making them via 3D printing. One can take advantage of the new developments in imaging, simulation, for example, to copy and mimic the exact design of the human body, or be more specific with the patient or personal medicine. Several things that are commercially produced these days. 3D printing is used in the dental industry, in the prosthesis devices, as well as hearing aids. And for example, 3D printing allows one to change the design of the infill or the bone density, for example, when one is trying to replace bone, which is different from the craniomaxillofacial surgery requirements all the way to orthopedic designs. Of course, 3D printing goes also into manufacturing of cars. This is the one of the first cars that was demonstrated here at Oak Ridge National Lab, where they're able to make new designs or resurrect old designs, such as the Cobra, based on 3D printing alone, or lightweighting of automotive engines, aerospace, etc. So what I've been driving at to this point is that 3D printing is advantageous because it allows complexity together with materials design to improve function and also the economics of production. And so here is a summary of the different 3D printing methods, from SLA based on lithography or photopolymerization, to fuse deposition modeling, which is used to 3D print plastic by melt extrusion, and even analysis of metals and use of metals and ceramics for printing. Here is a list of what is 3D printable, from metals to different polymeric materials, ceramic materials, and even organic materials, or even food. And that means there's a rich plethora of analytical methods that will be needed to optimize these materials that will be used for 3D printing, not only to optimize materials, but failure analysis. One of the things that we have used as a goal in our own projects and facility is to understand why some materials work and why some materials are better. And that means by stressing these materials to testing, one can then or use analytical methods to understand what are the modes that resulted into a materials failure as well. Now, polymer science, for those of you who would like to know the properties of plastics, really is a hierarchy of properties. What we know as polyethylene, which Regine showed very well in terms of analysis, are commodity polymers that form the base of this pyramid. So polyethylene, of course, is derived from petroleum products. On the other hand, the PEEK, PAEK, and other high-performance polymers form the apex of this pyramid, are based mostly on condensation polymers. Here is a Ashby-like type of diagram which shows that the cost and the tensile strength can be a combination of thermoplastic polymers versus that of thermosets. Thermosets will be your epoxy, your polyimide, phenolic, and polyester resins. That means at the right combination of processing and price, one can obtain the optimum strength and price ratio. And here is a collage of the possible applications of 3D printing in various industries, from marine to aerospace, consumer, and electronics. Now, nanomaterials can come in many forms, and a number of them are widely commercially available. Carbon nanotubes, graphenes, nanoclays, metal oxides, nanofibers, cellulose nanofibers. It may interest you to know that a number of products today contain nanomaterials, even though they are not widely classified as nanomaterials but as chemical additives. GC mass spec pyrolysis is interesting in that it allows you to analyze not only the volatile additives, the polymer themselves, but you can look at insoluble derivatives. Nevertheless, both carbon-based and non-carbon-based, organic and inorganic, can be distinguished in most cases by a combination of GC mass spec pyrolysis, NMR, and X-ray photoelectron spectroscopy. Of course, GC mass spec pyrolysis offers a way of exactly identifying the components, both on the organic polymer side and some of the charred components, let's say based on graphene and POS or silica-based type of components. Graphene, for example, is of a high interest to us because this combination of graphene and graphene oxide have been shown to have good mechanical properties as well as antibacterial properties. Here is a summary of the 3D printing projects we have done through the years, from polyurethanes to rubber to acrylate polymers, silicone composites, the use of nanocellulose on composites, and the 3D printing of high-performance polymers such as PEEK and PPS. So with the remaining time I have, I will show you two projects where we have applied GC mass spec pyrolysis, in fact, to analyze what we have or what properties that we can synergistically match with the composition and the performance that we observe. So rubber, for example, can be classified in many ways: natural rubber or synthetic rubber, elastomeric, thermoplastic elastomeric rubber, or thermoset elastomeric rubber. And some of you are familiar with the classification or acronyms of these materials, from SBR to SBM to EPDM. I will not, of course, be giving a review of rubber, but rather focus on one elastomer that we use. We investigated the use of polyurethane thermoplastic elastomers based on isocyanate and polyol chemistry. So just a short review based on this diagram shows that a typical polyurethane will be made from a hard and soft segment that is afforded by the use of a polyol or a isocyanate that can be your hard segment. The polyol produces the amorphous character, and the hard segment, the crystalline character based on the use of TDI, MDI, and other types of applications. Moreover, most plastics usually contain plasticizers to enhance their processability. And so the question is, can we analyze polyurethane that is used for 3D printing using GC mass spec pyrolysis? As you can see here, TPU and other polyurethane-based elastomers or even thermoset elastomer-based reactions are very important industrially. They can be found in a lot of car parts, engineering parts, machine parts, etc. On the other hand, TPU is also a very important biomedical grade material that can be used in a number of implants, prosthesis devices, artificial heart, or even resins for dialysis. So this project, in particular project, we have used the combination of graphene oxide as a reinforcing material in thermoplastic polyurethane. We first prepared the graphene oxide and thermoplastic polyurethane together with the polylactic acid compatibilizer by solution method. This allows us to prepare a very homogeneous mixture, which we can then evaporate the solvent and end up with a plastic material, a polymer material that we can prepare a filament. To verify the presence of graphene oxide, we use a technique called Raman spectroscopy to look at the D and G bands of the graphene and the oxidation state that it was used in the mixture. So after preparing this mixture, evaporating the solvent, and then doing an extrusion to prepare the filament, we then 3D printed these devices. And as you can see here, various forms, elastomeric property is confirmed. The color is black because of the graphene oxide loading. We were able to then test the different amounts of graphene oxide and its material properties. So graphene oxide then should enhance the property, the thermomechanical properties, and the orientation of 3D printing or 3D printability is an important parameter because 3D printing is a layering technique, an additive layering technique. Therefore, the direction of printing, parallel or perpendicular to the bed, makes a difference. This was exhibited when we tested the material for compression modulus, showing that the S and L compression or the parallel versus perpendicular are two different thermomechanical properties. Moreover, the tensile strength, tensile properties are very different too, depending on the direction as shown as in the row curves. In fact, the L specimen improved the compression modulus by 56%. The S specimen produced improvement of 167%, and overall, the addition of graphene oxide improved the performance of the 3D printed material. The tensile stress measurement or tensile modulus measurements, in fact, showed that at 0.5 weight% of graphene oxide, we obtained an optimum tensile modulus property, not the 5 weight%, mind you. What this implies is that the nanostructuring, even at a smaller amount of graphene oxide, actually makes a difference in terms of the graphene oxide synergistic property. Moreover, these 3D printed materials are biocompatible, as shown by these NIH 3T3 cells or fibroblast cells that were easily grown on all the 3D printed materials with up to 5 weight% graphene oxide. So you may ask, what pyrolysis GC mass spec contributed to this project? Well, we use all of the materials, the graphene oxide, the PLA, the solvent with known compositions. And some we synthesize ourselves. So we definitely know the composition, we know the structure. But what is unknown to us was the polyurethane. We use a commercial polyurethane sample, which we have no idea on its composition. And as shown you, it produced very interesting results. Yet, if we try to publish such a work, whilst reporting only a commercially available material, lessens its impact. So in this case, GC mass spec pyrolysis was a key technique for us to evaluate this commercial sample. And as introduced by Rogin, one can start with evolved gas analysis or EGA to look at the various compositions on the material. We can then use a combination of single shot or double shot or hard cut to analyze any additives, the different compositions of the polymer itself. So it's very interesting that the polyurethane, of course, can have a combination of TDI, MDI, or aromatic or non-aromatic isocyanates. So you may ask, is IR capable of analyzing those things? The answer is no. TGA IR is not sufficient to analyze those things. Can we use NMR to analyze those different compositions? Yes, perhaps you can, but you have to do a lot of separation techniques to get to the bottom of the composition. In this case, a combination of EGA and again the appropriate techniques after EGA allowed us to get the answers that we need. And again, a review here is that the EGA is the first step in this analysis of the 3D printed sample itself or the polymer we use itself, followed by either using the single shot or double shot to distinguish the additives from the polymer, and then to analyze the polymer composition alone. Or we can do hard cutting, dividing the EGA to specific zones to get a further handle on the composition. And as you can see here, the F search engine is a very easy tool to look at a library of possible compositions without going through a specific analysis based on the mass ion peak or the different components based on the major fragmentation structures of the material. So to begin with, the EGA thermogram of the polymer looks like the plot on the left. That means most degradation have taken place by the time you reach 600 to 700 degrees C. So several major peaks there are of interest on the thermogram. We then did a flash pyrolysis just to verify the presence of the major compositions that are found in the material. And what you can see here is we did indeed found polyol compositions of the polyurethane. In particular, butane diol is present. We did observe the presence of dibutyl phthalate. And this is, of course, of high interest because the commercial polyurethane has to be processed and therefore they have to add plasticizers. And as you can see here, we even have a handle on the isocyanates that were used. But more specifically, by doing a technique called hard cutting, we can divide the zones, zone A, B, C, and D. A revealed us the presence again of the phthalate. Zone B revealed us the presence of the some of the butane diol as well as the MDI. So to review, if you look at the EGA, we divided zone A, zone B, zone C, and zone D in increasing temperature as well as windows. There are different windows. So zone C confirmed the presence again of the THF, butoxybutanol. These are components of the different polyols, as you can see, a mixture of them. On the other hand, the zone D confirmed as well the presence of these different fractions. So all of this was done with F-search. And at this point, we have actually done a complete analysis of the polymer and even the presence of phthalates on that commercial polyurethane that we use. Now, on the remaining time I have going to show you one way we have transformed this polyurethane into foam. Now, you may ask, why is this of interest? Polyurethane is processed as a plastic. However, polyurethane is actually well known as a foam. Matter of fact, I'm sitting on a polyurethane foam right now, and probably you are if you're using a cushion or came with your automotive seat. It's usually based on polyurethane. We took an unconventional route to produce a foam by converting a thermoplastic polyurethane produced by 3D printing and then softening it. The way the printing was done, this case, was not by FDM, but by a technique called viscoelastic paste extrusion printing. Basically, we prepared a paste and then 3D printed it by syringe extraction. Pretty much, this is how you would 3D print ketchup, or this is how you would 3D print cement, or this is how you would 3D print chocolate. And that means you pay attention to the viscosity of the material and also its curability. So in this case, we prepared a paste of the same polyurethane that we just analyzed. We added clay, we added some solvent. The clay was actually a rheology modifier, but as I'll show you later, it was key towards producing an interesting foam property. 3D printing allows us to control the material as well as the design. Rheology is very important because of the viscosity parameter. I will reserve that discussion in another time, but suffice it to say, we look at the shear thinning properties based on sufficient yield stress and storage modulus. The result is we were able to 3D print these samples, these grids with different opening, and at the same time, by leaching or removing the nanoclay using hydrofluoric acid etching, we were able to produce a very different material property of the same design. So the correlation of the grid size and the material property by removal of the nanoclay produce a very porous nature, open cell nature, as you can see on the 3D printed material. So you can see the picture above of the 3D printed material after this HF treatment, and this resulted in very dramatic changes in properties. We can characterize or correlate the compression modulus based on opening size, the compression modulus based on the ratio of the nanoclay and the material, and it pretty much tracked the opening as well as the nanoclay. The simple trend is the higher the opening, the higher the compression modulus rather, and then the higher the ratio of nanoclay, the higher the compression modulus. So other than giving those numbers, probably it's better to show you a movie of those properties. So as we 3D print these materials, you can see that they're very hard to compress with a smaller opening. However, with a larger opening based on 3D printing, you can see that we can compress them somewhat or bend them. And you can see the comparison between A and B. Now, the dramatic transformation is when we remove the nanoclay and produce porosity on these materials. So from A, it was transformed to C. Okay, so the same plastic material then became a foam. From B to D, different ratio. So you can see a different compressibility. So all of this would have been possible because we used TPU that we obtained commercially. However, the value of the TPU just became very important because GC mass spec pyrolysis allowed us to understand and analyze the composition prior to using them for 3D printing. Now let me skip this two in the interest of time and give you the last example. The last example, we actually use silicone. Silicone, elastomer, and adhesive. Silicone is an important class of polymer that is used for seals, adhesives, bioimplants, different elastomer components. We were actually interested in this silicone adhesive, a $6 product that you can buy from Home Depot. Some of you probably use it to caulk or to use for DIY projects at home. And I'll show you that this is a very interesting 3D printing material. Silicone elastomers are processed as rubbers. It can be based on LSR or low consistency elastomer and of course adhesives. So using a different viscous solution printing method, we basically connected the syringe, filled it up with this DAP adhesive, and then use a regular Ultimaker 3D printer to produce a 3D printed part. So in this case, we started by doing an EGA analysis of the commercially available DAP adhesive. Again, we found the dibutyl phthalate, but majority of the composition is simply the silicone itself. This is akin to reverse engineering of that commercial sample. And of course, we could have applied other methods, but just to show you that by F-Search library alone of the thermogram, by flash pyrolysis, we can definitely confirm the presence of the silicone PDMS material or polydimethyl siloxane. And the various oligomers or fragments confirm this based on the mass spectral analysis of the individual peaks. And of course, to do a reverse engineering, then we will look at other types of additives that went into this silicone. And of course, for proprietary reasons, I will not go to some of those results. Again, going to back to the importance of viscosity, we took this now analyzed commercially available silicone, 3D printed it, optimized it by comparing the distance between the surface, the opening, the pressure from the syringe, and the optimum viscosity. The bottom line is this is a very viable 3D printable material. The result is we 3D printed them with various opening sizes of the tip. You can see the quality, the higher resolution with the narrower tip. All of this is based on that commercially available DAP material, $6 from Home Depot. We can make very high resolution printing, and I can even make our very own silicone tennis ball. And lastly, we have played around with a technique called SLA to 3D print a silicone material based on an acrylate derivative. We can 3D print them using this technique. This is based on photopolymerization, a combination of the acrylate monomers, dicross linkers, and initiators that we use. And we can 3D print objects like this and this. The 15% silicone polymer loading actually gave it a different elastomeric behavior versus a monolith. For lack of time, I will not be able to show you the results we have. We can basically reverse engineer the resin, that commercial resin that we use for 3D printing, as well as confirm the presence of other additives that were used on this project. Again, by doing so, we dramatically improve the impact factor of our work. Instead of just reporting a commercial sample, we can actually report what was used in that commercial sample. And I will skip this last part. This simply shows that we have used graphene oxide as a nanomaterial to improve this SLA 3D printed part. We have another project right now on using GC mass spec pyrolysis to analyze the presence of graphene oxide and its role in 3D printing and coatings as well. So I'm ready to conclude. What we have done and what I've tried to show to you is 3D printing and polymers as the future of additive advanced manufacturing. Most commodity polymers used for 3D printing are commodity plastics. I've shown a differentiation between what an elastomer, a thermoplastic, and a thermoset will be. I hope I've convinced you that in this case, GC mass spec pyrolysis was very important for our projects because it enabled us to analyze some of the commercial samples we use in these projects that have been published, reported. Case, the right use of the techniques allows us basically to reverse engineer, quote unquote, these materials for our own purpose. And in the future, you may, of course, contact me and ask more questions about our work on 3D printing, as well as other projects in coatings, adhesives, and so on. So with that, I'd like to thank you again, our audience, and of course, give back the table to Lauren for any QAs. Thank you.
Fantastic. Thank you so much, Dr. Advincula. It makes me think we just passed Valentine's Day. Maybe next Valentine's Day we'll be giving each other 3D printed chocolate. All right. So just as he mentioned, we're gonna dive into the Q&A portion of the webinar. Just a reminder, you can type your question into the module in the webinar control panel. And if there's a specific person you want to ask the question towards, feel free to include it. All right, let's dive in. The first up, it looks like this one is for Dr. Advincula. What are the major components of polymers and additives in FDM filament for 3D printing?
So let me start with the major polymers that are 3D printed these days. A lot of them are, again, basically commodity polymers. PLA, polylactic acid, is common. ABS, acrylate butadiene styrene polymer. Nylon, polyesters, polycarbonate. They're quite used heavily. On the other hand, you can even 3D print engineering polymers like peak pike to a certain degree. Now, we have found that a number of them are blends. Blends meaning they contain other polymers, as well as we have found the presence of additives, plasticizers on a number of them, because when you prepare these filaments for 3D printing, they have to be processable first in filament manufacturing. So a lot of them are simply compounded materials that have been used for a long, long time in the injection molding industry.
Fantastic. Okay, so we have another one that came in, and this one I think would be for Terry Ramus. Terry, in order to perform the heart cutting technique, are there any additional accessories required?
Well, the heart cutting technique, which of course can be best thought of as sequential thermal slicing of the sample, it needs to, what we need to do is thermal slice a region of the sample, say from 100 to 300 degrees as an example first. So we need to refocus all of the pyrolysates and additives that are removed during that thermal slice. To do that, we have to have the microjet cryotrap accessory. And that accessory then focuses the component so we can get a high resolution GCMS separation of just that portion of the sample. And there is a second device called a selective sampler. That allows us to take a thermal slice and throw it away because we may, for example, be interested in 3 thermal slices, but not the pieces in between. So going back to the question, the accessories that can be used to give you full heart cut capability in addition to the pyrolysis GCMS would be the cryotrap accessory and the selective sampler accessory.
Fantastic. Next question. This one I think might be good for Dr. Advincula. What methods did you use to elucidate the additives from the commercial silicone sealant?
Yes, so in principle, an old method would have been to do a Soxhlet extraction to do separation of the insoluble and soluble parts. And then on the solid part or insoluble part, you will have then to do IR or, to a limited degree, other types of elemental analysis methods or even the use of pyrolysis IR. And then, of course, the liquid, you have to determine the separation method to use, the solvent and purification, or even chromatography or column chromatography to separate components. That's the old method, and we have actually done that on several projects. The beauty of using the pyrolysis GC mass spec is we don't have to do all those methods at all. We simply load the sample on the pyrolyzer. We can get the EGA. Out of the EGA, we can do a single shot just to look at the components of the additives and polymer present, or a double shot to separate any volatile or any low molecular weight components, and then analyze the polymer itself. So in this case, the adhesive is mainly based on silicone. So to sort of analyze that silicone further, we definitely saw or able to look at the different monomer compositions or even copolymers that might have been used. And that can be done using the double shot method, focusing only on that window. And then finally, of course, by being careful on which zones that you separate for your hard cutting, you can further analyze or have an idea on what fragments might be or portions of your composition might be of interest to you. Another is that by doing the EGA in combination with TGA or thermogravimetric analysis, you can even do calibration to somewhat calculate the percentage composition of those components present in a commercial adhesive.
Awesome. Next question. I think this one would be for Regine. How much sample do you need to perform the pyrolysis technique?
That's a good question. This technique does not require too much amount of sample. Typically, when we are performing a bulk pyrolysis, we recommend about 100 to 200 micrograms of sample that you just loaded in the sample, as Dr. Advincula was mentioning. However, depending on your application, and if you're only interested in the additive and lighter portion of your sample, you can actually place more in a sample cup, because at this point, all the heavier and polymeric compounds remain in a cup, so you're only performing the thermal desorption analysis.
Fantastic. I have another one here. This is probably for Terry. How is this? Can this technique be used for performing competitive deformulation analysis?
Well, the technique is really quite amenable to that. The first step in the deformulation process would be to do an evolved gas analysis, and that would show us what would be evolving from the sample over a full temperature range, typically from 100 C up to 800 C. By the time we get to 800 C, all the organic has been removed from the sample. And this would show us a series of humps, if you will, that would look like a derivative mode thermal gravimetric analysis. And so from that, we can get some initial idea of what sort of additives or small molecules there are versus what polymeric materials there are present. And in addition, if it's a blend, we can sometimes then see multiple polymers within that blend. Then once that's done, then we can do a series of single shot and double shot analyses to look at the additive in the polymer regions. And then finally, the final step then would be to do a hard cut and to look individually at each of the regions of interest for the most specific identification. And then the last step would be to go through and perform quantitative experiments. For example, what are the concentrations of additives that are present in the sample? So that would comprise really a very nice deformulation of a complex polymer.
Fantastic. Let's see. The next one I have here, this little one looks like it's for Dr. Advincula. How do you differentiate between rubber, plastic, and thermoset by GCMS pyrolysis?
So first of all, yeah, you have a clue just by visual observation or how you feel about the material. Certainly, you can confirm the thermomechanical properties as well, or simply heat it up. So by GC mass spec pyrolysis, one of the ways you can distinguish a thermoplastic, most typical thermoplastics degrade by 300 degrees C. Thermosets, on the other hand, can degrade at a higher or even high performance polymers. Most elastomers as well degrade at a lower temperature compared to the high performance polymers. Of course, chemically, that is your best bet. The chemical nature allows you to classify certain classes of monomers, reactive ingredients that are obviously part of either a thermoset, a thermoplastic, or an elastomer composition. If, let's say, you are looking at natural rubber, then you will see components based on polyisoprene components. If you're looking at polyurethane, most polyurethanes, again, a composition of polyol and polyisocyanate. The reactants used for making a foam versus a thermoplastic polyurethane are quite different, simply because of the nature even of the presence of urea composition. Another is that elastomers, you can look at a class of thermoset and thermoplastic elastomers. Thermoplastic elastomers would be that of your um, SBS rubber or even polyurethane thermoplastic elastomers, having more compositions, again, of polyol and your hard segment, the MDI, TDI, or various aromatic isocyanates. So I would say it's a combination of the thermomechanical properties, the chemistry, you're familiar with the product, and of course, confirmation by GC mass spec pyrolysis. It's not possible to use GC mass spec pyrolysis alone, especially if you don't know the chemistry behind or have a clue on what could probably be the best composition of the product that you have.
Fantastic. All right. So it looks like I know we're running a little long, so I'm just going to choose two more questions here. The next one here, it looks like this is a good one for Regine. Regine, are there any standardized methods using the frontier pyrolyzer?
Yes, actually, there are some ASTM methods. One of them is for analyzing the regulated phthalates in PVC. That's ASTM D7823-18. And this method is specifically based on the thermal desorption mode of operation for actually doing the quantitative work on the phthalates from the PVC and other polymers. We also have another method for IEC, International Electrotechnical Commission. That's the number is 62321-8. That one is also for analyzing quantitative phthalates in polymers.
Great. And then the last one here, Terry, I think this is a good one for you to answer. What are some differences between the frontier pyrolyzer and some other pyrolyzers that are available?
Well, the primary difference to look at first would be the mode, the design and the mode of pyrolysis. So the frontier pyrolyzer uses something called the vertical drop microfurnace. So it can be best thought of as a furnace region that's preheated to a sample of interest, say 600 degrees C. And the injection or the initiation of the analysis comes about when you then drop the cup with the sample by gravity into the preheated furnace. So the placement of the sample, the introduction of the sample, and the temperature that the sample sees are all very reproducible, and that's what results in the high precision and the very good reproducibility from sample to sample. Other kinds of technology, one is based on a filament technique. You can think of this as taking the sample in a quartz tube and placing it essentially inside the filament of an incandescent light bulb, in a platinum filament, so to speak. So that analysis is initiated by turning the switch on and energizing the filament, and that filament then heats the sample. In that case, you're heating it up in a transient way in which the filament then passes its energy through the quartz tube and to the sample. So that technique is more dependent upon relative heat capacities and heat transfer properties. And then the final technique that's used is based on a Curie point. And essentially the sample is wrapped into a foil that can be heated by an RF frequency, and the sample, it's much like the filament in that the device is energized and the foil is heated up to its Curie point at which it stops, and it remains at the temperature that is a property of that Curie point of that particular foil. So in that case, you would then use a different foil for each particular temperature that you wanted to achieve. So those are the three basic modes of use.
Fantastic. All right. So I want to give a big thank you to Dr. Advincula, Regine, Terry. Thank you so much for your time today. I want to thank everyone who joined us today. Joining a webinar the morning after a holiday. I know it's never really that easy, but you were all troopers, so thank you all so much. As a reminder, as registered guests, you'll get an email within the next few days with a link to the recording, so you can watch it again and look at some of the graphs and stuff that Regine and Dr. Advincula were presenting. And of course, we encourage you to visit Quantum Analytics' resources page on lqa.com for future webinar details. And we have a really rich library of recorded on-demand sessions, so take a look at those. And we want to thank everyone again, and everyone have a great day.